welcome grade 12s to physical science, and we are delving into chemistry today. We are going to look at the big ideas of the rates of chemical reactions. We are going to do an overview and hopefully be able to delve into those areas where we struggle to understand, so that at the end of this we'll have a really good understanding of the fundamentals of rates of chemical reaction. Let's have a look at the overview. So here we have a concept map of the basics of rates of chemical reaction. We have a look at definition of rate. We, from there, have a look at factors affecting the rate of reaction. Factors that affect the rate of the chemical reaction will have a direct impact on what the graphs look like. Ways to measure rate, that is in the laboratory, so the practical ways of measuring rate will also have a direct implication on what our graphs look like. And then we have this interesting theory called collision theory. And collision theory is used to explain the factors and how they affect the rate of reaction. And we also use the collision theory to explain what is happening on this graph, the special graph that is called the Maxwell-Boltzmann distribution curve. Our graphs are really important because those are the pictures of what's happening in a chemical reaction, and so we're required to know what they are, and we have to be able to read off of them a value. So we're talking about quantitative values to be able to calculate various calculations problems, and also to look at them in a qualitative way and describe what is happening in that reaction. So we have energy profiles, which you probably have seen in grade 11. They are classically shaped. We have graphs from the experiments that are done in the laboratory. We have rates of reaction versus time, and then we have this very interesting Maxwell-Boltzmann distribution curve. So we are going to be looking specifically today at graphs of experiments and what they look like, how we measure, and how that impacts the shape of the graph. So, interpreting graphs from experiments, the shape of the graph that is drawn really is dependent on what we measure. So we have two pictures here, and the one picture is showing you how we measure a reactant that is being used up. So a decrease in mass of a reactant, and that has to happen per unit time. We're talking about rate of reaction. So how fast is the reaction happening? It is per unit time. It's a really important thing to say. Per unit time, it is telling us immediately that we are talking about rate and how fast is a reaction happening. So when we look at the decrease in mass in this apparatus, it is per unit time. We measure it in a conical flask. You can see that on the scale. The scale is then measuring the decrease in mass, and the gas that is being formed can escape. So we are only measuring the decrease in mass of this reactant. The second way that we can measure is in a closed system. You can see here that there is a plug in that conical flask. That means it's a closed system. No gas can escape. A gas is being produced in this reaction, and it is measured. The volume of gas that is being produced is measured in a very precise way using the syringe, and the gas pushes that syringe out, and the gratings can then tell us how much volume of gas is being made or produced per unit time. There is a third way that we can measure the rate of reaction, and we can do that by looking at the change in color that occurs. So this is the kind of apparatus that you would use. You're looking at a precipitate, a solid that is being formed. It makes the solution milky, or it is a suspension. Tiny particles of solid are suspended in the solution, in the liquid, and that cross that is sitting underneath the conical flask will become less pronounced, will start to fade. This way is more of a qualitative way of looking or measuring at rates. We are very interested in the quantitative way, which is measuring values, because then we can calculate. Here we have a reaction of zinc and hydrochloric acid. It forms a salt zinc chloride and hydrogen gas. Now the question here is, when does the reaction stop? We have two graphs. The one graph is measuring the mass of reactant, so that reactant is going to decrease as the reaction progresses. The second graph that we're looking at is the increase in volume of the gas that is being produced. So we're looking at the product and the volume of that. So one of these reactants is going to be a limiting factor or reactant. The other one is going to be in excess. And when we talk about something which is in excess, it means there's so much of it that there will be some left over in our reacting flask. So one of these things will be limiting, one of them will be in excess. I'm saying that the hydrochloric acid will be in excess, and so all of the zinc will be used, solid will be used. Let's look at this graph, the first one, which is measuring the zinc that is being used up. You will see this line, which is in green, is around about where the graph line becomes parallel to the x-axis. And when that happens, it means that the reaction has stopped. One of the reactants has been used up and there is no more left. The reaction has stopped. And so when we see that on the graph, the lines parallel to one another, the reaction has stopped. With the volume of gas being measured, it is going to increase, the volume of gas is going to increase to a certain point, and that's this point here, again, where the line is parallel to the x-axis. Parallel, the lines are parallel, the reaction has stopped. No more reaction happens. Let's move on to how we can interpret the gradient of these kinds of graphs. So gradient in terms of maths is a change in y value over a change in x. And so if we look at the y-axis here, this is in volume, so it is the change in volume over the x-axis, which is the change in time, and that is the rate. So the gradients for these graphs will tell us how fast this reaction is happening per unit time. It is the rate. Again, we're looking at the same equation. I'm drawing, or I have drawn, a tangent to each of these sections of a graph. So you'll see there's an initial stage, there's a middle stage, and there is a final stage. And this first tangent over here is pretty steep. It's showing you that the rate of reaction is fast. In the middle section, this tangent has flattened out a bit. Our slope has decreased, and it means that the rate of reaction has slowed down. It has decreased. In our final stage, if we look at this tangent, again, we go back to what we've said previously, that this tangent is now parallel to the x-axis, to the time axis, and so the reaction has stopped at that green circle. It is no longer happening. So grade 12s, how do we write that in words? How do we describe the gradient? Remembering that the gradient or the slope is the rate of reaction. So in the beginning, initially, you have a steep slope, or it's the steepest slope or gradient. It means a really high rate of reaction. Then what happens is the gradient or the slope becomes less steep, and that means that you have less volume of gas is being produced per unit time. So less volume of gas per unit time. If we have a look at the shape of that graph, it looked like this. And so you can see that this is a typical shape for when we are collecting product, the volume of a gas that is being produced. When that gradient starts to decrease, it means the rate of reaction decreases. Finally, when the line is parallel, so the line of the graph is parallel to the time axis, to the x-axis, no more gas is being produced, that reaction has stopped. It means that one or more of the reactants has been used up. Let's move to another way of talking about rate of reaction. We are asked to calculate the rate of reaction in a quantitative way. So what we talk about in words is the qualitative way, explaining what's happening to the gradient or the slope of a graph. Now we are required to work this out using our formula. Now, this formula is not given to you in the information sheet. So you have to know this. So the average rate, or in other words, the gradient, is the change in volume for this particular experiment over the change in time. There it is there. And because we're dealing with average rate, we want to use values from the start to the finish. So here is the finish. How do I know that that is the end of the reaction? Because the line is parallel to the time axis or the x-axis. So that is the final result, the final volume. Over here in this green circle, that's the start of the reaction. So that is my initial value. I read them off the graph. You can see here I have a value of 500, and at that space there, that green, that is equal to 0. I substitute it into my equation. I've got the final volume minus initial volume divided by the final time minus the initial time. I've popped in my values over there, substituted them in, and I get an answer of 8.33 centimeters cubed per second. Centimeters cubed because my volume, according to my y-axis, is measured in centimeters cubed, and my units for time on the x-axis is seconds. What happens if we measure the mass of reactant that is being used up in the reaction? Our graph is completely different. You can see here that it's a curve. And if I draw a line with a ruler, it's the yellow line there. If I draw that line, you will see that this curve is actually a negative gradient or a negative slope. And for that reason, when I'm calculating my slope, my gradient, I will find that my rate is equal to a negative change in mass over change in time. Negative is really important. It has to be written there. You must write that in. If you are measuring the decrease in the mass of a reactant, your gradient for that particular graph is going to be negative. So negative has to be placed in front of the formula delta M over delta T. Let's look at what's happening to the rate of the reaction by drawing the tangent to the various sections of the reaction. So here's the tangent to the initial stage of the reaction. You can see that it is really steep. That means that the rate of reaction is fast. Our middle section, or middle stage, we're drawing the tangent to that section, and you can see that that line, the slope, has decreased. It's not as steep. It means that the rate of reaction is slowing down. It is decreasing. At this point here, you can see that the reaction has completely stopped. I've circled it in green. It has completely stopped, and I know that because the line of the graph is parallel to the time line, or the x-axis. How do I write that in words? I know that the rate of the reaction is going to have a negative value. You can see here negative because the line is negative, the slope is negative. The formula is change of mass over change in time. So I need to bear that in mind when I am writing a description of the rate of reaction. So initially I've got a really steep slope or gradient. It means the rate of reaction is the fastest. As the rate of reaction becomes less, as it decreases, that steep or that slope or gradient is going to become less steep. And that means that less mass of reactant is being reacted or used up per unit time. And finally, when those two lines are parallel to one another, the line of the graph is parallel to the time axis. No more reaction is happening. The reaction has stopped, and so no more mass is reacting. And that is because either one or both reactants has been used up. If I look at this particular graph, the shape, when I am measuring the using up of the mass, in other words, the mass is getting less and less and less as it is reacting, that is the particular shape that you're going to get. How do I calculate the gradient, particularly using the numbers that I'm reading off the graph? I have to remember this formula. So average rate is equal to negative change in mass over change in time. I keep that negative there. You can see it as I'm working through my calculation, the negative remains. Final mass is this mass that is denoted by the red dot. I read it off the graph as 0.2. Why do I choose that space? I choose that space or that place because it is the end of the reaction. I'm trying to find the average rate of a reaction, so I have to use the final value as being where the reaction has stopped, it has ceased. I use the initial mass as the one that we really start with at the beginning of the reaction. I pop all my values in, 0.2 minus 3 over 16 seconds minus 0, and my answer is 0.175 grams per second. Why that unit? Because on my y-axis I am measuring the decrease in mass with grams and I am measuring time in seconds. There is one last graph that you might come across, and that is the graph that has its end right on the x-axis. And what does that mean? That means that the mass of the reactant is the limiting factor and that it is all used up. This is where we have no more mass left. There is no more reactant. It is all used up and the reaction has stopped. Right, grade 12s, I hope that has given you a good overall view of these particular graphs relating to the volume of gas that is produced and what it looks like, as well as the graph that comes out of when we measure the mass being used up, in other words, the reactant being used up. It is time to have a brain break. Welcome back, grade 12s. Let's do a quick recap. To interpret graphs and collect data from them, we really do need to know the definition of rate. And so here is the formula. We need to know it off by heart. It's not in the information sheet. If gas is collected, then we have an equation or a formula for rate, which is the change in volume over the change in time. If we are measuring a decrease in mass, that means that our gradient is going to have a negative value, and so for our formula for rate, we need to put rate is equal to negative change in mass over change in time. Let's just move on to the next concept map. So we are in the second half going to have a look at the factors that affect the rate of reaction, and we are going to talk about the collision theory and how do we write that in a way that makes sense to whoever is reading our answers. So the factors that affect the rate of reaction, there are 6 of them. Temperature. An increase in temperature increases kinetic energy of molecules or particles, and so their rate of reaction is going to increase. Surface area. Surface area is to do with solids, and so if solids are ground up into a powder, it means there's a greater surface area and there is more particles, more molecules that are able to then participate in collisions. Concentration applies only to solutions and to gases, and we have this formula for concentration, which is the number of moles over the volume of gas or solution. So an increase in concentration is going to increase the rate of reaction. Pressure applies only to gases, and there we use Boyle's law, which if you take an area or a volume of a gas and you make it smaller, the particles have got less space to move in, even though the number of particles remains the same. Their collisions are going to increase because they've got less space, and therefore there's an increase in pressure. So by decreasing the volume of a gas, the space in which a gas is in, you are going to increase the pressure, and therefore the rate of reaction is going to increase. Catalysts are really interesting, and catalysts provide an alternative energy pathway, and so the rate of reaction increases. The last one, number 6, is the nature of a substance. So if a substance is inert, it's not going to react very well, it's old and slow, and if you have something which is a product, an atom or a molecule that is energetic and reacts well, those will be in group 1 or group 17. You know that the rate of reaction is going to be high. So what do we need for an effective collision? So that's a big word because effective collision comes up often. An effective collision means that there is a high number of collisions happening, that the kinetic energy of the particles has to either be greater than or equal to the activation energy of the reaction, and then the orientation of the particles has to be correct. In other words, the orbitals that contain unpaired electrons have to overlap one another. Those are the 3 requirements for an effective collision to take place. So how do we explain all these factors in terms of collision theory? There are specific things we need to say for each one of them, and then there are things that are the same that we need to say for each one of them. So if we have an increase in temperature, the average kinetic energy is going to be increased. So the higher the temperature, the faster the particles are going to move. Particles collide more frequently. What does that mean? It means that there are more collisions per unit time because we're talking about rate. So unit time has to be placed there. There are more effective collisions per unit time. Therefore, there is a higher rate of reaction. In our next factor, surface area, collisions take place on the surface of a solid. We know that. So larger surface area, more collisions, more effective collisions per unit time, faster rate of reaction. Are you starting to pick up the things that are the same? If there's an increase in concentration, it means that there are more particles per unit volume, so there are more collisions per unit time, more effective collisions per unit time, and a faster rate of reaction. The next one is an increase in pressure. Remember, this happens for a gas, and we've spoken about Boyle's law. If there is a decrease in volume, there's an increase in pressure. There are more particles per centimeter cubed or per volume, more collisions per unit time, more effective collisions, and the rate of reaction is faster. A catalyst is a really interesting one because it lowers the activation energy, providing an alternative energy path. And so that more particles will choose this different effective energy path. So the same amount of product is being formed, but there are more collisions per unit time, more effective collisions per unit time, a faster rate of reaction. So only the time frame changes. The product is formed faster. Back to our map. I hope that this has given you a good overview of the collision theory and how it is involved in explaining how factors affect the rate of reaction. We hope to see you next time, grade 12s.